Hi everyone, our project is 24x7 contactless respiratory rate monitoring using infrared depth cameras. We started from a very practical problem. Post-operative, chronically ill, and elderly patients need continuous respiratory rate monitoring, but what they usually get is intermittent spot checks and uncomfortable contact sensors. Nurses count breaths every few hours, or we use belts and probes that patients don't like and often take off, especially at home. In our proposal, we asked a simple question: can we get continuous RR and apnea information from a single depth camera pointed at the torso while the patient stays under a blanket? Because this is an IR depth camera, it only returns distance values per pixel, not a full RGB image of the person's face or room. That means we can see how the chest is moving without capturing identifiable visual details, which is increasingly important as hospitals and families worry about video privacy. Our goals for the semester were: track 3D torso motion with an Intel RealSense depth camera, convert it into a clean respiratory waveform and RR estimate, expose everything through a clean real-time dashboard, and build a pipeline so it can later support features like respiratory patterns or posture. On the poster, the left side tells a clinical story and problem. The middle shows our RR pipeline and the final dashboard. The right side highlights technical advances, the waveform, and conclusions. One important theme is what we didn't do yet. We have not built a large supervised machine learning model. Many recent camera-based RR and apnea systems train classifiers on sizable label datasets. For us, actually collecting that kind of dataset, recruiting subjects, putting reference belts on them, synchronizing depth and ground truth turned out to be the hardest part. So this semester we focused on a robust, interpretable signal processing pipeline that works with limited data and can later feed ML models once the formal clinical study is in place. With that set up, I'll hand it over to Amber to walk through how the pipeline evolved from our original idea to what you see in the diagrams.
Thanks, Abel. I'll start with the RR pipeline in the bottom because it captures the journey from our proposal to the final system. We began with the straightforward approach from our proposal: depth camera to fixed chest ROI to band pass filter to peak detection for RR. In early experiments, that's exactly what we implemented. Draw a manual box over the torso, average depth in that box, and then look for the breathing peaks. It worked if the box was perfect and the subject stayed still. But in practice, it was very sensitive to placement and the posture and how the blanket creased. Sometimes blanket edges dominated the signal. Next, we tried grid-based ROIs with FFT scoring, picking the cell with strongest respiratory band energy that led to cells flickering from frame to frame and overemphasized high gradient edges. We also tested PCA breathing modes, hoping the dominant component across the torso would be respiration, but PCA mixed breathing with other motions from limbs and blankets. Those negative results pushed us towards the more structured pipeline on the poster. The final pipeline on the poster, if you see, first is sensing. We streamed Intel RealSense depth at 640 by 480, 15 FPS, convert to meters, and smooth with Gaussian filter to reduce sensor noise. The next is auto torso ROI. Instead of fixed box, we select the closest depth slice, run connected components, and pick the blob with the best center weighted depth score, closer to the camera and nearer the frame center. We constrained that ROI to about 25 to 60% of the frame area and smooth it over time so the torso box is stable even if the blanket shifts. Motion guided mask. Within that box, we keep a downsample temporal buffer and compute an FFT at each pixel. We integrate energy in the 0.1 to 0.5 Hz respiratory band, weighted by spatial gradients, and get a frequency aware motion map where real breathing stands out from flat regions or random motions. Thresholding at connected components give a breathing blob, and we smooth it over time as a probability mask. That's the non-rectangular region you see inside the box. Respiratory signal and RR. Now for each frame, we average depth between the motion blob to get 1D signal, apply a band pass filter, and then use a Hilbert transformation to obtain instantaneous phase and frequency. This phase-based RR idea is similar to Hilbert approaches used in ballistocardiography and other physiological signal. We convert frequency to RR in BPM, smooth it with Kalman filter, and also compute a 60-second moving average as a trend, uh, as clinician wouldn't recognize. And the quality in apnea, for each 8-second window, we look at RR average, a simple SNR metric, and RR stability. Those feed a 0-1 confidence score that surface how trustworthy a session is. In parallel, if breathing amplitude drops below a fraction of baseline and RR approaches 0 for at least 8 seconds, we raise an apnea event and timestamp it with the local time zone. Now, if you look at the figures, the dashboard figure in the middle shows system as a clinician would see it. A depth image with the green auto ROI or yellow manual ROI and a motion blob contour. A torso panel where breathing motion is color coded so you can visually confirm the pattern, and the status bar with instant RR 60-second average confidence and any apnea timestamp. If you look at the waveform panel on the right, that's 20-second respiratory depth trace after band passing and outer clipping. You can see clear cycles at the breathing frequency rather than jittery spikes, which is what makes the Hilbert and Kalman steps behave nicely. This is also the signal we would later feed into any ML model for pattern classification and anomaly detection. Now, what was the challenge and what's novel? So, two big challenges shaped our choices. First, data in ML. We couldn't realistically collect the large label data set needed for the supervised apnea or pattern classification in one semester. Many recent contactless RR systems rely on that kind of data from control studies. Rather than training a small, unreliable model, we built a strong deterministic pipeline as a foundation for future clinical data collection. Second, real world robustness. Fixed ROIs and naive variance maps were too fragile under blankets and changes and posture changes and global PCA picked up a lot of non-respiratory motion that pushed us towards a center-weighted auto ROI plus a frequency-aware motion mask, which is less common in depth only besides bedside setup compared with fixed chest patches or purely global maps. Now, compared to prior work, the novelty in this combination here. One is the center weighted area constraint auto torso localization. Second, a gradient weighted respiratory band motion mask that produces a sticky non rectangular ROI. The Hilbert phase based RR with Kalman smoothing and an explicit confidence and apnea layer. All designed for a privacy preserving depth only dashboard running in a real time in 15 fps. With that, I'll hand back to Abel to close with the big picture and where we would go next from here.
Thanks, Amber. To close, I want to connect back to the original proposal and where this could go. In the proposal, we promised a real time RR dashboard and accessible architecture and early apnea detection. Over this semester, we iterated through fixed ROIs, grid selections, PCA, and finally arrived at this motion guided, phase based pipeline that now runs live with the RealSense camera. For someone new to this area, the main message is with one privacy preserving depth camera and no contact sensors, we can already get a continuous respiratory waveform, RR estimates, and a confidence score, and a basic apnea flags while a person lies in bed under a blanket. At the same time, we're very aware of limitations. We still need a formal clinical study with multiple subjects, reference belts, or capnography, and proper labeling to quantify accuracy and to support machine learning models. So the next steps are run the clinical study and report metrics like MAE, and Bland-Allman plots across positions and blanket conditions. On top of this pipeline, explore ML for respiratory pattern classification, posture estimation, and activity breathing coupling once we finally have enough data. In short, this semester we built the spine for a contactless, privacy-preserving RR monitoring system, robust signal processing, and an interpretable dashboard that's ready to plug into future clinical research and machine learning work. Thanks for listening. Happy to go deeper into any part of the pipeline, the challenges we ran into, or ideas for collaborating on the clinical study piece.